Okay, so welcome back. um, basically, kind of the gist of yesterday's very long lecture, right? At the end of all of that, kind of the the moral of the story is one big difference between the situation in PDE and ODE is that unlike ODE, where you might remember, right, in the first chapter of whatever notes or whatever text you used, there was this big, nice existence and uniqueness theorem, right? So you might not be able to state it off the top of your head, right? But under some reasonable assumptions, there was this big existence and uniqueness theorem for ODEs that were reasonable. Now that theorem, of course, doesn't actually finding explicit closed form solutions to an ODE. That's a different story entirely, but it told you something about the existence of such things. So unfortunately, no thing like that exists for PDEs. So there is no kind of analog to that sort of thing. So we're kind of the approach that we're going to go about is basically assuming that we have a solution to a given PDE and see what sorts of properties it might have and see if we can find a general solution that way, right? We're not guaranteed to be able to do this, of course. There may be no solution, as I mentioned in the previous lecture. There may be a solution that we can't find a closed form expression for, right? We may be we may be able to show that a solution exists, but not be able to actually explicitly find it. That's also possible. If we're really, really interested in actually answering specific questions about the thing, maybe we can say something about the behavior of the solution, either from the PDE or through some other kind of analysis, without having a closed form expression for it. But if we actually, want, say, some very specific numbers for this thing to spit out at us, that's where approximating the solution via numerical methods would come in. Okay, but thankfully for us, we're going to be in a case very often in this course where we can actually find, closed form expressions for these solutions. So naturally, we're going to start with first order PDEs, and in this case, we have beautiful method, the method of characteristics that I mentioned previously, that's going to allow us to, when we're lucky, when we're in the best case scenarios, we're going to be able to actually find closed form expressions for general solutions, or at least when we can't find something like that, we'll at least be able to find or derive very, very specific behavior or properties that the solution would have, right? And so anyway, this is our goal. Now, as it says in the so this is chapter 2 in the textbook. And naturally, since a first order PDE involves, what does it involve, right? It involves like independent, so some independent variables, the unknown function u itself, and then first order partials of the thing, right? That's what it involves. So thought of in this way, this is some relation that involves the directional derivative, right? So this is essentially some relation involving the directional derivative of our unknown function u. And maybe it involves u itself, but the idea is it involves the directional derivative in some way. So if you are a bit rusty on remembering exactly what the directional derivative is for a multivariable function, or how it is computed. We'll talk a little bit about that, but if you need to refresh your memory, you can look at section 1.3 in the appendix. So section 1.3 in the appendix can refresh your memory here. We're going to use this a lot because a lot of our intuition about what a first order PDE says is going to come from the fact that it's a statement about the directional derivative. So in the simplest cases, for instance, it's some statement that something involving the directional derivative is equal to 0. So that's this is going to be key for our understanding here. So as I've already said, our main tool in chapter 2, right? Our main tool for first order PDEs is the method of characteristics. So what is the method of characteristics, right? What is this? We are going to try to develop the intuition behind this as much as possible so that this isn't, or this is minimally confusing. The textbook warned several times about this, that I think the biggest hurdle to overcoming some difficulties in computations when it comes to method of characteristics is that the notation can be slightly confusing. And there's not much getting around that. It's just a matter of getting used to it and basically practicing so that you're not confused. I think the textbook says, you should be in control of the notation instead of letting the notation be in control of you. But that the only way to come about that is to just practice a bunch with these things. And so anyway, what is the method of characteristics? What's kind of the best way to think about this? Let's say that we have a PDE in two independent variables. So say we have PDE in variables x and y. Okay, so two independent variables. And say that we want to solve this on some domain, omega. So say we wish to solve this PDE on some region omega. Let's be specific here. Instead of some omega, let's actually specify a specific omega. Let's say we want to solve this on the upper half plane, right? So this is the set of all ordered pairs x, y in the plane such that y is greater than or equal to 0. Okay, there we go. Okay, so let's draw a picture here. Right, here's my upper half plane omega. It is all of the upper half plane, including this boundary, right, including the x-axis. Okay, so this is included, and it doesn't include any of these ordered pairs where y is negative. Okay. All right, so this is what my picture looks like. Right? Here's my omega, is this upper half plane. So then what is the method of characteristics? The idea is that if this PDE being a first order, so this is a first order PDE. This is a first order PDE. So what we are looking for are curves. Okay, we're looking for curves such that if we are specified some data at a point on the boundary here, then we are allowed to determine the value. So if we're specified, so here, let's say that a solution to this PDE in question. Notice I haven't even written out a PDE. I'm just saying some first order PDE. We'll say that u of xy is the unknown function that solves this PDE. Okay, so I want to find the general solution, right? I want to find a u of xy that solves this PDE, and it's a general solution, so any solution to that PDE has to be of the form that I find, right? So what I'm seeking, okay, what I'm seeking is a curve such that all I need to know is some boundary value or initial value or some data, right? So in this context, it's a boundary value. So I know, say, a boundary value here, and I seek a curve. I'm going to draw it like this, intersecting the x-axis at this point. Okay. And this curve that I seek is a curve such that knowing this value here on the boundary is enough to determine the values at all other points along this curve. Okay, so knowing this determines all of the other values of u along that entire curve. Note, not along the entire upper half plane, but along the entire curve. Okay, so then, for instance, here, right, would be some other initial point. I'll call it x sub 1, 0. All right, here's maybe another curve that has this same property, that knowing the value on this boundary right here tells me the value of a solution along this entire curve that intersects the boundary at that point. So then what is the idea here, right? So the idea, and this is, I'm not being too rigorous here, I'm just kind of speaking freely. The idea is that the PDE degenerates into an ODE along such curves. Okay. Now, that is to say, if we can find curves having this property, then we could say, in a sense, the PDE degenerates into an ODE along such curves. What do I mean by that? Because what would it mean if I say that knowing the value of the solution at this point here on the boundary determines the value of the solution anywhere along that curve? You could think about this in the ODE sense of knowing, for an ODE, right? So imagine now an ODE, right? Knowing an initial value for that ODE, right, determines the value of the solution, right? That's that initial data, right? So this is for a first order ODE. That initial data specifies one of that infinite family of solutions, so that you know that initial data, right? You know what that initial data is. That allows you to, it determines the entire behavior of the solution, right, in that sense. But this is just along a single curve. So then how is this method going to yield a general solution, u of x, y, at any point in the upper half plane, right? Our goal is to be able to describe the value of a solution to this PDE at any generic point in the upper half plane, not at a point along, say, just this curve or just that curve. So what kind of brings this together? So first of all, where does the name method of characteristics come from? Okay, these curves are said to be characteristic of the PDE. So these are characteristic of the PDE. Meaning, in a sense, these curves taken individually are saying something about the character of the PDE, Okay, and now you might say, well, but these are just, you're just picking out curves here. How does that give you the whole picture? The second idea, right, is if such curves, right, if these curves fill out omega, then a generic point a generic point, uh, I should say, you know, x, y, and omega lies on some characteristic curve or some characteristic. That's what's meant by filling out. So then what is the idea here? Now, this picture might look a little bit weird to you at first because, as you'll notice, right, we have a two-dimensional region, omega, right? And so our u of xy is actually defined on this region. So if you thought about graphing this thing, of course, you're familiar that, you know, the graph of a function of two variables would be, you know, if you're lucky, it'd be like some surface sitting over this region, right? So when I label these points with u values, I'm saying that the value of u is specified here. I'm not saying that this point is the value of u, right? It's that the value of u sits, if you like, above this point. We don't think about that too much. We're not gonna, you know, we're not going to think about that too much in this context. We're just going to say, well, I'm specifying these values here, right? So I want to find the value of u at this generic point xy. So if you like, you know, the actual points I'm labeling are these. All right, let me get rid of u there. So these are the actual points, and I want to find the value of u at these points that I've specified. Okay. All right, and so if these curves fill out omega, then some generic point lies on a characteristic. And so I need data specified at this point to tell me the value of the solution u at any point along this characteristic associated to that point. So if I have that, then I am good to go. So basically, what I would need is to specify values along this entire boundary. And if I am in the situation that I can actually fill out my region with these characteristic curves or these characteristics, then in this way I can find the value of my solution at a generic point because a generic point lies on some characteristic. That is the idea. Okay. Now that, if we kind of think about this, right? This, you know, this seems like we're asking a lot here, right? So it really seems like we are asking a lot. We're assuming that we can do all of this stuff. So what is it that I'm saying? Again, when I seek these characteristics that fill out my my domain, I'm saying the PDE degenerates into an ODE along all these curves, and so somehow there are ODEs floating in the background, right, that determine these characteristics or determine the behavior of the solution along these characteristics, right? And so in some sense, I'm saying that this first order PDE is like a family of ODEs that are paired together, that are coupled together in a way. Okay, and so the question then, so what is it that I want? I want to be able to find all the characteristic curves. I want my characteristics to be non-intersecting. We'll talk a little bit more about that in a while, right? So first, I seek such characteristics that are non-intersecting. Why is that a problem? Well, you might say, you know, you kind of remember some issues about when we talked, you know, or when you first learned about ODEs, when it came to thinking of these like curves filling out your region, or you plotting trajectories, right? The problems with intersection in your in your existence and uniqueness theorems, it was that this violated uniqueness, right? Because you had two like solution curves intersecting, but they, you could specify different initial data, and you basically get non-uniqueness of solutions, right? So specifying the same initial data, you would get two distinct solution curves, and that was no good. Here, we're going to see examples of what happens when we have characteristics arising from a PDE that end up intersecting somewhere. For now, we're just going to hope that we're in this perfect situation that the characteristics are non-intersecting. So that's the first ask. So we want them to be non-intersecting, and we want them to fill out omega, like I said here. Okay, so that's the first thing. Next, we want these characteristic curves to start at a point on the curve where the data is provided. So in this example, where our omega was the upper half plane, the data that we needed was on this boundary. But actually, we could specify this data on like a curve in the upper half plane. In fact, in general, as long as we're specifying it on some subset of like the closure of omega, here, if we were to specify this on like omega plus boundary, like we have here, somewhere on here, so like say some curve in the upper half plane, as long as we do this in a way that basically fills out omega, then we're happy. Okay, so it doesn't have to be the x-axis, but oftentimes in this course that's exactly what it is going to be. It's either going to be all of the boundary or some subset of the boundary, and usually, well, in a lot of cases, that's going to be some coordinate axis. Okay, it's going to be the x or y axis or something. Okay, and so we would like, for each point in this domain, the unique characteristic curve which passes through it only intersects this x-axis once, right? So for any point that I choose in omega, we want this to only intersect the x-axis once, right? So second, we want a unique characteristic through a generic point in omega to intersect the set where we're specifying our data. I'm going to say the x-axis here. It need not be the x-axis. It can be any set where you specify the data here to intersect the x-axis once. Okay, again, this is so that we don't have ambiguity introduced by one characteristic intersecting in multiple spots, so I'm not actually sure which point is the thing that specifies the behavior, right? So that's what I want to avoid. And then, of course, if I'm claiming that the PDE is degenerating into ODEs along all these curves, and somehow I need to solve those ODEs in order to determine the solution or the behavior of the solution at a generic point, then I want to be able to solve those ODEs, right? So third, I want to be able to solve the ODEs in question. So I want to be able to solve the ODEs in question. Okay, that seems like a reasonable request, right? Of course, this is using the data provided on the x-axis. Again, doesn't need to be the x-axis, just needs to be some subset of the closure of our domain. Okay. So if we can do this, then as I said, what's the idea? Let's assume that we've done all of that. Then, in order to find value of the solution at a completely generic point xy in this region, a completely generic point has a unique characteristic that passes through it. That unique characteristic only intersects the x-axis once. There it is, right? I have data provided at this point. That data allows me to solve the ODE that tells me exactly the behavior of that solution corresponds to the behavior of the data at that point of intersection between this unique characteristic curve that passes through that point intersecting the x-axis here. So this is how we do it, right? We have generic point. Generic point lies along characteristic. Characteristic intersects the x-axis. The x-axis, we have data specified. The behavior of the solution matches the behavior of that corresponding data specified at that point of intersection. So that is how this process works. You can draw several pictures to illustrate this, but this is probably one of the most basic and easiest to see. Don't worry if the intuition behind this stuff, isn't immediate, because we are going to be repeating it over and over and over again. It's not easy to basically come to this realization or to understand how this goes. And so to alleviate that a little bit, we're going to do some examples. Now again, it seems like we've demanded a lot from this request, right? So we have requested these three things at least that I enumerated here. So then the question is it reasonable to do this, right? We have some big assumptions here. So this is not going to work for all PDEs. In fact, I specified that we were dealing with a first order PDE, but if you had the question, does this process work for second order ODEs or second order PDEs? The answer is no. It doesn't. So for instance, it doesn't work for the heat equation or diffusion equation. It doesn't work for the Laplace equation. But if we restrict our attention to first order PDEs, this is a statement about directional derivatives, as I mentioned. And so since these directional derivatives give rise to ODEs, then these first order PDEs kind of behave like a bunch of ODEs kind of pasted together in a sense. You'll get the picture of how this works when we do this. Now, what can be rather surprising is that this actually doesn't just apply to the linear first order PDEs. It also applies to nonlinear PDEs. There are some complications that arise, but this general process can be adapted to work for nonlinear PDEs as well. So it's first order PDEs as well. So this is a really powerful and a really beautiful thing. The other question is, does it matter how many independent variables? I did it for 2, but does it matter if I had a first order PDE in variables, say x1, x2 out to xn? Is that okay for the method of characteristics? Yes, not a problem. Okay, this can be adapted for however many independent variables. It doesn't matter. Okay, so the number of independent variables doesn't affect this since it's first order. That's the main thing. Okay, and so let us have a look at some specific examples. Okay, so some specific examples before we state the characteristic equations. So let's start with the following. So let's say we have the PDE that is A u sub x plus B u sub y is equal to 0. No other data. This is the PDE and that's it. Okay. So we'll let A and B here are just real numbers, right? And I want to find all functions u of x, y that satisfy this equation. So I want to find all u of x, y satisfying this PDE. Okay, so how do I do this? Remember what I said about this being a statement about directional derivatives, because this is a first order PDE. So what kind of statement about directional derivatives is this? Recall that the gradient of u is the vector containing the x and y partials, right? Okay, so this is the vector containing the x and y partials. A and b are just two real numbers, and so I can rewrite this. Right, this equation can be rewritten as the vector AB dotted with the gradient of u, and that is equal to 0, right? So here's my vector. This is my gradient, right? It contains first order partials of u. AB is a vector. These two things dotted, that's exactly this expression, right? That's just the dot product of these two things. Is equal to 0. Okay. Now, recalling my directional derivative, I'm going to stick to the notation that's used here. It might vary with the notation you use about directional derivative. So recall that the directional derivative of u. Here, let's not use vector notation on u. That doesn't make any sense. So this is the directional derivative in the direction of d of the function u, right? What is this defined to be, right? This is, so if d is a unit vector, right, then this is just the gradient of u dotted with this vector, right? And so let's say that our vector d is our vector AB times 1 over its length. So if this is, we'll say 1 over the square root of a squared plus b squared, okay, times the vector AB. So if we have normalized our vector, of course we can always do this, right? We can always make any given vector we have, we can always find a vector pointing in the same direction that's a unit vector just by scaling by its length. Only vector we can't do that with is the 0 vector, and we don't care about the 0 vector here because that's not a very interesting equation, 0 equals 0. So, so we're fine to do this. If D is my vector pointing in the same direction as AB but made into a unit vector, then really what is this statement, because this is equal to 0, this is the same as saying that the directional derivative of u in the direction of d is 0, right? Now, that is to say that, note, the right-hand side is 0. This means that scaling by the length of the vector doesn't affect this at all, right? I can always multiply by that scalar, multiply both sides by that scalar, and it's not a big deal. So if I multiply both sides of this equation by 1 over the length of AB, then I get exactly this thing, right? Where, you know, so this is, so D is the directional derivative. Remember, we only consider directional derivative for unit vectors, right? Because all we care about is the direction specified by this vector, not its length. So this is the directional derivative. Again, if you're confused about directional derivatives, just look up that section in the appendix. Okay. So then this PDE is really the same as saying the directional derivative of u in the direction specified by the vector AB is 0. But remember, the directional derivative, so this is Calc 3, this is a Calc 3 statement. The directional derivative being 0 in some direction is telling you that the instantaneous rate of change of the function in that direction is 0. Hence u is constant in that direction. Okay, so this tells me that u is constant in the direction of the vector AB. That's exactly what I'm told. So, how are we doing this, right? Let's go back through this. We have a PDE that we want to solve. We want to find all u satisfying this PDE. So what do? We assume that we have a u of xy that satisfies this PDE, okay? And then working on that assumption, we see what it would have to look like, right? Now it might be that if I gave you some awful PDE like that, right? That initial assumption may be wrong. There might not be a u that would satisfy that PDE. Maybe you'd say, okay, I assume there's a u that satisfies this PDE, and then you derive a bunch of properties, a bunch of consequences of that thing, and see, oh, actually this is contradictory. I couldn't have had such a u. But in this case, we see right now, what does this mean? It means that I have some u that has to be constant in the direction of this vector AB. So let's draw. Remember, we have absolutely no restriction here. This is the only PDE. We have no initial data specified, no boundary data, none of that stuff. So as far as I know, I'm solving this on all of R2, right? No restrictions. So if I draw a picture, okay, of R2, then I have the vector AB, whatever that vector is. So if here is the point AB, we'll say, sitting in the first quadrant, then here's my vector. Of course, D is going to be pointing the same direction. It's just unit, whatever. Here's my vector AB. But then this expression, I was told that u is constant in the direction of AB. So what does that mean? Remember, u kind of sits above the plane, right? The values of u sit above the plane. And all I know is that this u is constant in this direction. Well, what does that mean? That means that if I specify, remember, right, vectors, it doesn't matter where a vector sits, right? A vector can sit anywhere. It's the direction and length that matter for vectors. But here we're talking about a direction. We know that u is constant in the direction specified by this vector. And so what that means is that if I have, say, a line here, right? Maybe I should use a different color. Here, let me get a blue pen. Where did I put my blue pens? Here we go. Okay, so this line, for instance, is, well, I tried to make it parallel to this vector. This line is parallel to that vector. Here's another one that is, and another one. Of course, we could just extend that vector as well to make another line, but I want to leave the vector here so that you can still see it. Here's another one, right? They don't have to be equidistant from one another. I can make them. There we go. There's more. Here's another one. Okay. All of these trajectories I've drawn, all these lines, are lines in the direction of this vector AB. Okay. And so since u has to be constant in the direction of AB, u must be constant along these lines. So what we know is that u must be constant along these lines. And so we have lines in the plane. That is, we have curves in the plane, right? They're just very simple curves. So we have curves in the plane that tell us what? That specify the behavior of u along the entire curve, right? So then we have these lines, and of course, once we know a point where the line is, we just need to know that it is in the direction of AB. And now we know that if we specify a value for u on one of these lines, it must be constant. Here's a warning, though, right? So quick warning. Maybe I'll put a star here. it must be constant along the lines. But that doesn't mean that each line or it doesn't have to be the same constant along each line, right? So U must be constant along each line. But the constant can change from line to line. All right? Let's think about this for a second, right? Again, this PDE, going all the way back here, this PDE told us that a function satisfying this satisfies that its directional derivative is 0 in the direction specified by AB, which means that it's constant in the direction of AB. So it's constant along any such line like this. But of course, it can change in any other direction, right? So in this direction, the value of U can change. It could go up, it could go down, it can change. Okay? And so necessarily I have to include the possibility that the value of U can change from line to line. But along these lines, once a value of U is specified, so if I would say specify the value that U has here to be 10, then everywhere along this line it would have value 10. But if I specified that the value of U here is 7, then along this line it would have value 7. Along this line it would have value 10. In between in some other direction, right? Or in, like I said, it doesn't have to be in between. It can be in some other direction. It can change, right? It can change. And so that shouldn't be too surprising because we know that just like in the case of ODEs, for PDEs, if we're looking for a completely general solution, we have some degrees of freedom, right? And we've already seen from the previous lecture that these degrees of freedom, rather than being parameterized by arbitrary constants, are instead parameterized by functions, right? This is like kind of our canonical example of these things, parameterized by functions. Okay, so here is the thing then. So first of all, such lines can be written as, we can write these lines as bx minus ay is equal to c. Right, for some c. So for some constant c, where the choice of c denotes our choice of constant, right? So this choice of c determines the line, right? So if I choose c, then this fixes the line here, right? So where the choice of c determines the line. Okay. i.e., right, if 2 points x1, y1, and we'll say x2, y2 lie on the same line, then what has to be true? Well, bx1 minus a y1 is equal to b x2 minus a y2. Actually, this implication goes in both directions. So if bx1 minus a y1 is equal to bx2 minus a y2, then they also lie on the same line. So this goes in both directions, and so the c determines the line. So if I choose, once I choose a c, that uniquely determines which line I've picked out here. Okay. And so the value the solution takes on a line is not dictated now by the PDE. I don't have to think about the PDE anymore. I can just say, well, the value the solution takes at any line, since, I drew finitely many lines here, of course, because I have finitely much time to draw them, but there's infinitely many lines that completely fill out our region R2. So if you haven't realized it by now, I'll go ahead and spoil the fun, that these lines are the characteristics for this PDE. So this is our first example, our first explicit example of what we mean when we talk about finding these characteristics. So let's think about this again. I have found curves such that specifying a value of the solution at a point on the curve, let's imagine for a second that I now change the problem slightly and say, all right, we're seeking the solution on just the upper half plane and the x-axis, right, which is exactly the solution I had before. I could specify a value for u at all these points where my characteristics intersect the x-axis. That would specify my solution on the entire line. There are infinitely many of these lines, of course, and these lines fill out all of omega, which is the entire omega here is all of R2. So these lines fill out all of R2. They're non-intersecting necessarily. Through any point, there is a unique such line that passes through that point, right? This is like planar geometry, if you like, right? That there's a unique line between 2 points. So there's a unique line, any point in my region, there's a unique line passing through it here. All these lines are non-intersecting, and they fill out the entire plane. So if we go back to our requests, our first, second, and third requests here that we made, all of those are met by this. And so we truly have found characteristics for this PDE. So by what I said previously, this should be enough, right, to solve this PDE. This should be enough to give us a solution. So we've seen that a choice of this constant c determines the line, and now the value that we specify for u on each line determines the value for u, like on that entire line, right? So the data that's specified determines the entire line, but we've just seen that specifying the constant specifies the line. And so to each such constant, I can assign a value to u. And this value, of course, varies from line to line. But then what am I seeking? I'm seeking an object that takes in a value c and spits out some other value, right? So for each c, to that c, I assign it a value. What kind of object is that? Right? What kind of object takes in some real number and spits out some other real number? Well, it's a function, right? It's just a function. It's just a real valued function. And so here is our degrees of freedom for this problem. It's just a real valued function. Thus, u of xy is equal to f of c, but what is that? I don't like that, right? But each c is a bx minus ay, right? So u of xy is f of bx minus ay for some function f. Now, of course, I want this f to be like smooth enough so that the PDE makes sense and all that, so let's not get too crazy with the f's that we choose here. But the idea is for a reasonable function f, here's my completely general solution. And this process that we followed has shown that really it has to be in this form, right? So the only requirement for u to be a solution to that PDE that we wrote is that it's constant on lines that are parallel to this vector. That is it. We have just reformulated that sentence, that statement, into a PDE, and it turns out that that PDE is exactly the same, right, as this statement, that it is constant on lines parallel to that vector. Okay, so since the PDE dictates the directional derivative of u has to be 0 along lines that are parallel to it, then this general solution has to be of this form, right? It has to be a general function of lines that look like that. Okay, and so that is the general solution. So what is the general solution here? Let's write it again. All right, general solution u of xy is some function f of bx minus ay. And now that we have said this, you can check, go back, and this will be quick exercise for you following along here. Go back and check that this thing for some nice function f, well, it doesn't have to be super nice, but some function f, that f of bx minus ay satisfies this PDE. Okay. So this is as simple as this example may be, this is a very, very important example because it shows you basically how this method of characteristics works in kind of the simplest way. Okay, but even so, it's important to understand this example because it really gives you a lot of insight into kind of what it is we seek to do. We basically seek to replicate that just for much more general PDEs, for PDEs that are a little bit nastier, right, where we can't make such powerful statements that it's constant along these lines. Okay, so there's an alternative way of doing this that involves something that's going to be reused in this textbook and in this course for the remainder of the semester, which is the following. So here's an example of an alternative way, so an alternative solution to the previous problem. And a notational trick. That will be repeated over and over again in this course, as I said. Okay, so if we have a dependent variable or a function that depends on independent variables x and y, we denote it, of course, as u of xy. Okay, so it takes in an ordered pair of real numbers x and y and spits out a real number u of xy, right? So what if we want to do a change of variables, right? So what if I want to do a change of variables? So just as an example, right? So here. So this is, yes, this is a sub-example. This is an example in an example. I can't help it. So here's u of xy. We'll say that u of xy is something that looks like this. We'll say it's 4x plus y squared plus x minus y squared. Now, you may remember from Calc 3 that there were things of this type that when you were asked to do any kind of serious computations with them, you noticed that, boy, wouldn't it be great if this expression and this expression, right, were simplified, changed to different variables, right, say like u and v, right, so that this becomes u squared plus v squared, which is a simpler thing to deal with algebraically, and you kind of proceeded from there, right? So that's kind of our idea here. The way, of course, that we think about this is we say that xy gets sent to 4x plus y squared plus x minus y squared. Okay. Okay. So let's say that we want to describe this in new variables, right? So let's in new variables, which we'll call Kasi and Eta. Okay, so we'll say here. Let me do a better Kasi. So here's Kasi. We'll make Kasi 4x plus y, and we'll make Eta x minus y. Okay. So in the new variables Kasi and Eta, what is the thing in question, right? If we're trying to view what it is that's going on here, we would have Kasi and Eta being sent to Kasi squared and Eta squared, right? So Kasi squared plus Eta squared. That's what we would get here. Now, here's the thing, right? If we have defined u to be this thing, then technically, if I write u of Kasi and Eta, since u of xy is this thing, and x and y here are variables, so it doesn't matter what I plug in there, right? It follows this form. So technically, if I write u of Kasi and Eta, what that means is this is 4 Kasi plus Eta. Why does my Eta look so bad there? Squared plus Kasi minus, Eta squared. That's what this is. But for notation's sake, and because I don't want to, I want these things to be prettier and nicer. I'm going to, come up with a new dependent variable name, right? So technically, this is what I have here, right? So then what I would need to do if I want to denote this function, which is the one that I care about, the nice version of this, technically I would need to define some other name, right? Okay. I would need to maybe call it W or Omega or whatever, right? Something like this. But the problem is that really what I want to do is basically just do this change of variables so that I can get the computation I want via chain rule, right? Or chain rule type computation. And so what we want to do here is, rather than redefining a new function and getting kind of lost in that, when all we really want to do is do some kind of computation involving the chain rule here, what we will write is u of Kasi Eta, but it won't be this, it's going to be this thing. So this is an abusive notation, no doubt. This is an abusive notation, but it's an abusive notation that is useful, and so we're going to do it. And that's that. So if you see a problem where this occurs, and you're like, wait, this is no longer the same function. Don't worry too much about it. As I said, this is like a very standard abusive notation. If this bothers you, just come back to this fact. This will help you remember that. Oh yes, okay. This is just I'm just doing this as kind of a shorthand little trick. Okay, and so how can I use this abusive notation, this little change of variables trick, to solve this previous PDE? So back to my example. Okay, so let's introduce two new variables. Let's do Kasi is we'll do say ax plus by, and Eta is bx minus ay. And I just now noticed that I have everything zoomed. I have it zoomed out way too far, and I read it's actually not a Cassie in the textbook. It's a zeta. But you'll have to forgive me. I'm just going to call it Cassie for the rest of this example, and then I'll start doing zetas later. I actually think I can squiggle a Cassie better than a zeta anyway, so it's fine. Here's an example of a Greek letter that's way easier to put in tech than it is to write, of course. So anyway, so let's let Cassie be ax plus by and let eta be bx minus ay. And if we do this, then using the same argument we had before, then let's go back to the PDE here, right? Like our PDE was a u sub x plus b u sub y is equal to 0. Okay, let's actually compute this using the multivariate chain rule. So how does this work? So this is what we know in variables x and y. So what is u sub x now in terms of this new variable Cassie? Well, u sub x, of course, is the partial of u with respect to x, but using the multivariate chain rule, this is actually the partial of u with respect to Cassie times the partial of Cassie with respect to x plus the partial of u with respect to eta times the partial of eta with respect to x. Right? So this is the multivariate chain rule. If you don't, which is, if you want to review that in the Gulick text, this is section 13.4, I believe. So what is partial of u with respect to Cassie? I will leave that. Partial of Cassie with respect to x is a, so this would be a times u sub Cassie, right? Plus this is partial of u with respect to eta. Partial of eta with respect to x is b, so this is plus b times u sub eta. Okay. And then similarly, if I do this same sort of computation for u sub y, I get that this is equal to b times u sub Cassie plus minus, not plus, this is a times u sub eta. Okay, so you can verify if you want to. And so when we switch back into this, of course, so if a times u sub x plus b times u sub y is equal to 0, this means that 0 is equal to a u sub x plus b u sub y, but then a u sub x is like a squared u sub Cassie plus ab u sub eta plus b squared u sub Cassie minus a squared, minus ab u sub eta. So that ab u sub eta cancels with minus ab u sub eta, and this is equal to a squared plus b squared times u sub Cassie. Okay. And so I have 0 is equal to some real number times u sub Cassie, which means that I can just divide by it, it's not a big deal. U sub Cassie is equal to 0. And so this PDE in x and y reduces to the PDE that is just u sub Cassie is equal to 0. And of course we seek a solution in terms of Cassie and eta. And so we have an unknown function u we're seeking that depends on two independent variables, Cassie and eta. And we know that its partial derivative with respect to Cassie is 0. But what does that mean? By what we said in the previous lecture, what does this say? It means that it is constant with respect to Cassie, which means the most general form that it can take is a function of eta. So this means that our general solution, so this is our general solution, is just a function of eta, since its Cassie partial is 0. So our general solution is this. But wait, what is eta? It's bx minus ay. And so this is f of bx minus ay. Oh. So in terms of the original independent variables, this is actually the exact same. This is the exact same thing, right, that we found the normal way, right? Okay, so that's a good, it's kind of a good method for seeing how we didn't have to do this approach that we did with characteristics, right? We could have done a slick, we could have done kind of a slick sort of change of variables here to get this nice fact, but we see that this is just further verifying that what we did is actually correct. Okay, let's see what happens if we do the exact same example, but now we actually have an auxiliary condition, right? So here's our next example. Same example, but with auxiliary condition. So what are we going to have? Let's choose some specific numbers here. So let's say 3u sub x plus 2 u sub y is equal to 0. And our auxiliary condition is to specify that on the x-axis we have this data function x cubed. Think about what this means just in, let's go back to our picture here. Going back to our picture, we have data specified on the x-axis, right? So our data specified on the x-axis. At any point on the x-axis x, the data specified is x cubed, right? And that data determines the value of the function along the characteristic, the unique characteristic that intersects the x-axis at that point. Okay. So again, just if you need to, just think about what that means. Now, again, going back here, does it matter that I specified this data along the x-axis instead of, say, at level y equals minus 5, right, intersecting all those characteristics? No, it doesn't. So I could have specified data in another way, but this is just the way I chose to do it. So there it is. Okay. All right, so the good news, right, is that we know what a general solution to this PDE is ignoring the auxiliary condition. So I know what the general solution has to look like, but then this auxiliary condition should force a particular choice of function, right? That's the idea here, right? So we know the general solution is u of xy is some function. Here we have specific values for a and b, right? So this is f of 2x minus 3y for some function f, right? For some function f. Now we want to determine exactly what this f should be, right? So in a similar way to in ODE, when we imposed an initial condition, right, by taking the general solution, plugging in the value of the initial condition there, and then solving to figure out what it was that's going on, here we're no longer solving for a constant, right? We're no longer determining arbitrary constants, right, specifying constant values. Here we're determining a function, right? We're determining an arbitrary function. So let's see how this works. So by this auxiliary condition, we know that when u is equal, or sorry, when we are on the x-axis, which is when y is equal to 0, we know that this is equal to x cubed. But also, by the general solution, we know that this is f of 2x minus 3y. Here, though, y is 0, so this is f of 2x. Okay. So then how do I think about how this is doing? Now, we don't have to explicitly do it this way, although this is typically, especially if this is a more complicated expression here, this is kind of the best way to do it. The idea here is to say, okay, let me change variables really quickly, right? So let c be 2x, right? So let c be 2x. If c is 2x, then what does that mean? So x is, well, c over 2. All right. So then f of c, so we'll say f of c, why is that c so small? That bothers me. Let's do this. F of c is, if x is c over 2, then this would be c over 2 cubed, which is, oh, sorry, not squared, cubed. So this would be c cubed over 8. Okay, so the reason why I wanted to write it like this is just so that we can think to ourselves, okay, what does f do? You can read it off from this. It's just kind of hard to keep track of what it is that's going on here. That's why I do encourage you to do this, even if you think this is kind of silly to make a change variables like this. Let's think. F, according to this, f is a function that takes an input c and does what to it? It cubes it and then divides by 8. So f is a function that takes in an input and then cubes it and divides by 8. So what does that mean? It means that if our general solution f is a function applied to 2x minus 3y, what I know is that this is a function that takes an input, cubes it, and divides by 8. And so this function is actually 2x minus 3y cubed divided by 8. Okay. And so, quick practice. Check that this solves not just the PDE, but also the auxiliary condition. Right? Well, you can quickly see that it solves the auxiliary condition. You plug in 0 here. You have 2x cubed divided by 8, which is 8 times x cubed divided by 8. So it's just x cubed. So it definitely solves the auxiliary condition. You know that it's going to solve this, but just check, just for practice, right? Check that this solves the PDE plus auxiliary condition. Okay. All right. So I think that's pretty good for today's lecture. So I'm going to stop, and we'll pick up here in the next lecture when we do a couple more examples before stating the characteristic equations, and then we'll really get into kind of the meat of this for linear and semilinear equations. So anyway, I think it's important to see these other examples before we write out the characteristic equations, because with the characteristic equations, you might have a tendency to kind of get a little bit robotic about how these exercises are done, about how these computations are done. So I definitely think it's good to work through the early intuition for the simpler examples, because the intuition can be a bit harder to come by for the more complicated examples if you don't fully understand what's going on in these simple ones. Okay, so anyway, so that's what we'll do in the next lecture. So I'll see you all for the next lecture soon.